Then we'll continue this steady state error. Now the steady state error is calculated only for unity feedback. You know the reason. It depends upon the reference input or reference level, and it is only for stable system, because unstable systems we don't need to find any error analysis. Okay. Or you already know one more point of that. There is no steady state analysis. No steady state analysis for impulse response. You know that very well, because impulse response is having only transient term, no steady state term. Am I right? No. Impulse response is having only transient term, no steady state term, no reference level. Therefore, there is no steady state analysis for the impulse response. And the last one, and this is the steady state error depends upon type of the control system. The steady state error depends upon type of the control system. The steady state error depends upon type of the control system. Now you already know that the type of the control system the steady state error depends upon type of the control system, where that steady state error depends upon the type of the control system, where type of the control system is always obtained from open loop transfer function. This type is the number of open loop poles at origin. Is it right or not? The number of open loop poles at origin. But don't think that the steady state error is calculated for type. The steady state error is calculated for open loop. No. The steady state analysis is always for closed loop control system. This is the steady state analysis of closed loop control system. But that closed loop control system steady state error depends upon the type of the system. Okay. These are very, very important points for any competitive examination point of view. Steady state error is for unity feedback. Steady state error depends upon the reference input or reference level. Is only for stable systems only the steady state error calculation is possible, and no steady state analysis for impulse response, because impulse response is having only transient term, no steady state term, and it depends upon the type of the system. Once again, I will see the proof of this, because we have some points which we already known to you. Okay, so I will give one small example such that you can have a clarity of all these particular points. Okay, now first just note of this. Okay, students. Now there are total 5, and one more point also we have to add it very soon. Okay. Now we'll add very soon one more point. Now that is 6th point. Okay. What is that 6th point also we'll see. First we'll finish this. Okay. Then what is your steady state error formula? First you tell me. Now your steady state error formula which we are derived just now, and how much it is? The steady state error, which is nothing but the steady state error, which is equal to limit s tends to 0 s into r of s by 1 plus g of s. Now first you have this particular formula in your mind. Now this is the steady state error formula. Now I am asking one question first. Find steady state error for type 0 control system. Where is type 0? Where is type 1? Where is type 2? Type 3? Now that type of the control system is obtained from open loop transfer function. Now first you take a open loop control system. What is open loop control system? Now this is the open loop control system transfer function g of s, which is equal to k into 1 plus st1, 1 plus st2 and so on by s power n into 1 plus sta into 1 plus stb and so on. Now this is the open loop control system. The number of poles at origin in this open loop control system. Therefore, this is nothing but the type N control system. The number of open loop poles at origin. Now this is nothing but type N control system. The number of open loop poles at origin. Now this is nothing but the type of the control system. Okay, this is type N system, type N control system. Now I am asking a question. Find steady state error. Listen to the question carefully. Find steady state error for type 0 control system with different inputs. Okay, what is the question? Find steady state error for type 0 control system with different inputs. Now, whenever this is a type 0 control system, what is the meaning of type 0 control system? Now, this is n open loop poles available at origin. Therefore, this is type N control system. Now, I want type 0 control system, which is nothing but, now there is no open loop poles at origin. Now, therefore, this is type 0 control system. Now, s power 0, which is nothing but the 1. Okay. Now, this is a type 0 control system. Find steady state error for type 0 control system with different inputs. Why type 0? Because it depends upon type. Why input? Because it depends upon input. That's why I give these two relations. Okay. Now, with the different inputs means, now you start with case 1. Now, your reference input is unit step input. Okay. Now, what I am taking? Now, this is the unit step input. Now, I am taking as a unit step input. Now, what is R of S? Now, R of S, which is equal to Laplace transformation of U of t, is 1 by S. Now, the formula is available, input is available, type is available, then substitute in this formula. Now, what is the steady state error? Now, the steady state error, which is equal to limit S tends to 0, S into, what is R of S? Now, this is R of S. R of S is nothing but 1 by S. R of S is nothing but 1 by S divided by 1 plus G of S. 1 plus G of S. Now, this S cancel. Now, this is nothing but, can I write like this? 1 divided by 1 plus limit S tends to 0 into G of S. Am I not? 1 divided by 1 plus limit S tends to 0, G of S. Now, students, where is G of S? This is G of S, because this is type 0 system. Now, in this G of S, can you substitute S tends to 0? 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1, 1 into K. So, what is the final answer? K, which means that limit S tends to 0, G of S answer is nothing but a K. Am I not? Therefore, which is nothing but, this is finally 1 divided by 1 plus K. This is 1 divided by 1 plus K. Now, what is K here? So, K is nothing but limit S tends to 0, G of S. Limit S tends to 0, G of S is nothing but a constant K. But this is the constant K which is coming when we are applying a step input. Am I not? Therefore, this K is called as step error constant. This K is called as step error constant. This K is called as step error constant. Step is nothing but sudden change or sudden position. Therefore, this is also called as positional error constant. This K is represented as step error constant or positional error constant. This is step error constant or positional error constant. That K is represented as step error constant or positional error constant. Therefore, this K is represented as Kp. Okay, step error constant or positional error constant. This is the steady state error for type 0 control system with unit step input. Now, I am asking one question. This is the steady state error for type 0 control system with unit step input. Is it right or not? This is the steady state error for type 0 control system with unit step input. Can you tell me what is the steady state error for same type 0 control system with step input? Type 0 control system with step input. Now, the steady state error for type 0 control system with unit step input is 1 by 1. With step input means this is step equal to A. This is the unit step R of t, which is equal to U of t, which is equal to 1. Unit step input. Now, step input, this is A by S, A by. So, A by, because some constant, no? Therefore, this is the steady state error, which is equal to A by 1 plus Kp. This is the steady state error for type 0 control system with step input. Right? If it is a unit step input, this magnitude is 1. Okay. Now, this is the steady state error for type 0 control system. With unit step input and with step input also. Okay. Note down this. Okay. Now, this is the same type 0 control system. Okay. Same type 0 control system. Now I change the input because the steady state error depends upon input. If input is changing, steady state error is changes. No, we'll see that. Okay. Now this is unit ramp input I am taking. This is the unit ramp input. So this is nothing but R of t, which is equal to unit slope is into t. Now what is R of s? R of s is nothing but 1 by s square. Therefore, limit s tends to 0. S into R of s is 1 by s square. This is cancel one time. S is available. Therefore, Now 1 divided by s into 1 and s into g of s, and substitute s tends to 0. If you substitute s tends to 0, what happens? Now, which is nothing but 1 by 0 plus 0, 1 by 0. Now the steady state error equal to infinity. Now this is very simple proof. Previously unit step input. Now previously unit step input, how much is the steady state error you are getting? 1 by 1 plus k, some constant value. But now unit step input is changed to unit ramp input. Now what is the steady state error? Infinity. Now hence it is proved or not? The steady state error is changing when the reference input or reference level is changes. Therefore the second point is proved. Okay. The second point is proved, and which is very simple proof for this. When input is changes, reference level is changes. Now definitely the steady state error is also changes. Okay, whenever the reference level is changes, steady state error is also changes. This is steady state error for type 0 control system with unit ramp input. Note down this. Now I just change the question now. Now steady state error depends upon the type of the control system. Therefore change the type. Change the type. The steady state error depends upon type. Now this is type 1 control system. Type 1 means one open loop pole available at origin. Type 1 control system will start with unit step input. Now we'll start with unit step input. Type 1 unit step input. Therefore R of t, which is equal to u of t, which is equal to 1. R of s is 1 by s. Limit s tends to 0. S into R of s is 1 by s. S cancel. Therefore, which is 1 divided by 1 plus limit s tends to 0 g of s. Is it right or not? Now limit s tends to 0 g of s. Now where is g of s? This is g of s. Now in this g of s, substitute s tends to 0. If you, this is limit s tends to 0 g of s. Now what is this value? This is g of s. Substitute where s is there, substitute 0. Now something by this s is 0, something by 0, and what is this answer? This answer is infinity. Therefore this is nothing but 1 divided by 1 plus 1 divided by 1 plus, what is this answer? This answer is infinity. Something by 0, infinity. 1 plus infinity, infinity. Therefore something by infinity, this is 0. Now this is type 1 control system with unit step input. Now steady state error is 0. Previously same unit step input but type 0 control system. Previously same unit step input but type 0 control system, you can get the answer is 1 by 1 plus k. Previously constant. Now I am changing the type. Steady state error is changes. Therefore this point is also proved. Steady state error depends upon type of the system. When type changes, steady state error is changes. Note down this to it. I think now these 2 points are clear. The steady state error depends upon the reference input and steady state error depends upon the type of the control system. Now, same type 1 control system now will change the input. Unit ramp input R of t, which is equal to 1 into t. Now R of s, which is equal to 1 by s square. Limit s tends to 0, s into R of s is 1 by s square. Limit s tends to 0, s into R of s equal to 1 by s square. Now this is s cancel. Now this is nothing but steady state error, which is equal to 1 divided by s plus s into g of s. Now where limit s tends to 0, so can I write like this? 1 divided by s into, this is 0 plus, don't substitute directly 0 here, limit s tends to 0, s into g of s, because this is, don't substitute directly, this is 0 into something, it depends upon g of s also, right? So what should be this value? What is this value is important for us now. Now this is g of s. Now this is g of s is multiplied with s. G of s is multiplied with s means this s is also cancel or not? And then you substitute. After cancelling this n, substitute s tends to 0. S is cancelled. 1 plus 0, 1 plus 0, 1 plus 0, 1 plus 0, 1 into k. Therefore this answer is nothing but k. Therefore, which means that this is the constant k which is coming, limit s tends to 0, s into g of s. This is the constant k you can get, which is nothing but 1 divided by, this is k, some constant. Now this is the constant you are getting when you are applying which input? Ramp input. Therefore this is called as a ramp error constant. This is called as ramp error constant, and ramp, another name for ramp input is velocity input. Therefore this is called as velocity error constant. This is called as velocity error constant. This k is represented as kv, ramp error constant or velocity error constant. Therefore this is nothing but 1 divided by kv. Now the velocity error constant or ramp error constant. Now this is nothing but type 1 control system with unit ramp input. Now this is the steady state error for type 1 control system with unit ramp input. Now I am asking a question, what is the steady state error, which is equal to a by kv. This is for same type 1 control system with ramp input. Ramp means is having a slope. A is the slope of the ramp signal. If this is unit, therefore a equal to 1. Answers are changes. Okay, that's why you should be concentrate on slope is 1 or slope is something. If it is 1, unit ramp. If it is something, that something value you should be taking care here. That's why the answer will be changes otherwise. Okay, now note down. This is the steady state error for type 1 control system with different inputs, and this is velocity error constant kv or ramp error constant kv. Okay, note down. Okay. Now I ask one question, then you do it for that. Now this is a steady state error you calculated for type 2 control system with unit parabolic input. You do this, okay? Steady state error for type 2 control system with unit parabolic input. Now the steady state error for type 2 control system. Type 2 control system means now there are two open loop poles available at origin. There are two open loop poles available at origin, SS square. The type 2 control system means two open loop poles available at origin. Now this is unit parabolic input. 1 by 2 into T square. R of S is 1 by S cube. Therefore, this is 1 by S cube. Cancel one time, and this is SS square, and SS square into G of S. This is 0. Limit S tends to 0. SS square into G of S. Don't write directly S tends to 0 and this is 0. Okay. Now this SS square and multiplied with G of S. The value will depend upon G of S also. So first G of S should be multiplied with SS square. Whenever G of S should be multiplied with SS square, this SS square is also cancelled. SS square into G of S. So can I write like this? So limit S tends to 0, SS square into G of S is a constant K. So SS square cancel and substitute S tends to 0, 1 plus 0, 1 plus 0, 1 plus 0, 1 plus 0, 1 into K is nothing but a constant K. Now this is the constant K when we are applying a parabolic input. Therefore this is called as parabolic error constant. Parabolic error constant, and a parabolic error constant. The other name for this parabolic is accelerated input. Therefore, this is called as accelerated error constant. Accelerated error constant. This K is represented as Ka. Therefore, now the steady state error is, this is Ka, 1 by Ka. This is 1 by Ka. Now this is the steady state error for type 2 control system. Type 2 control system with unit parabolic input. With unit parabolic input. Now the question, unit means this slope is 1. So if it is a parabolic input, this is some constant, right? Now this is A by Ka. This is the steady state error for type 2 control system with parabolic input. Understand or not? With parabolic means this is A by 2, A by, A by, A by, A by, A by Ka. Unit means this A value equal to 1. Okay, anywhere. Unit ramp means A equal to 1, unit step means A equal to 1. If it is a step, that magnitude you should be considered. If it is a ramp, that slope you have to consider. If it is a parabolic, that constant value you have to be considered. Okay. Now this is the steady state error, depends upon the type. When type changes, error is changes. When input, reference input is changes also, error is changes. I think you have understand all these points which are very important. Now we will form a sixth point based on these particular relations. Now before that, you just take a copy of this. Now based on these particular calculations, then we just form one table. And sometimes in the questions he may ask this constants also. What is the ramp error constant? What is parabolic error constant? Or what is accelerated constant? And what is step error constant? Like that, sometimes he is asking constants also. Okay. So that constant he is asking, then you have a direct formula, use that. Okay. Now this is type 0 control system, type 1 control system, type 2 control system. Steady state error. Steady state error for type 0, type 1, type 2. Now unit step input. Now for unit step input type 0, type 1, type 2. Now unit ramp input. If it is unit ramp input, what is the steady state error? Now if it is parabolic input, what is the steady state error? Which we already calculated. Okay. Some steady state error we are calculated. First you do that. Okay. Now this is unit step input. This is unit ramp input, and this is unit parabolic input. Now students, you just see here, for type 0 unit step, which we already calculated, how much you are getting? 1 by 1 plus kp, you are already calculated. Now type 0 unit ramp is also calculated. How much you are getting? Infinity. Now type 1 unit step also you are calculated. How much? 0. Type 1 unit ramp is also calculated. How much? 1 by kV. And after that, type 2 unit parabolic is also calculated by you, 1 by k. But remaining parameters we are not calculated. Okay. Now what is type 2 unit step? We are not calculated. Type 2 unit ramp is also calculated, and unit parabolic type 0 and type 1 is also not calculated. We will calculate, not an issue. Okay. So this is the different types of the system, and this is the different inputs, and this is the steady state error calculations. Okay. Now there is no need of doing this lengthy derivation part, and there is no need to remember this equation and R of S, Laplace transformation, G of S. All these things are not required. Now I will provide one small shortcut method. You can remember that one, and you can get any answer in the steady state error. Okay. Now see, but based on this we can have one important point is nothing but the steady state error depends upon type, because when type is changing, steady state error is changes, and the steady state error depends upon input. When input is changing, steady state error is also changes. Therefore finally the steady state error depends upon the type of the system. The steady state error depends upon the input. So based on this particular point, the steady state error depends upon the input, and the steady state error depends upon type. Therefore I have a relation between type and steady state error. So this is the relation. Now I want to take type, compare with, now this type is compare with power of the input signal, power of the input signal, when the input signal is represented in power of the input signal in time domain. Power of the input signal in time domain. Then you ask one question, sir, what is the power of the input signal means? Now that's what I am writing here. Now this is u of t equal to 1. Now this is in time domain. Now time domain t power. What is the power of the input signal in time domain? T power 0. Now here this is unit ramp t power 1. This is the power is 1. This is unit parabolic 1 by 2 into t square power is 2. Okay. Now this is power 0, power 1, power 2. Now a type you should be compared with the power of the input signal, which means that now there are three possibilities here while doing this comparison. Now first possibility is type may be greater than, am I not? Now the type may be greater than power. The type may be greater than the power of the input signal in time domain. If the type is greater than the power of the input signal in time domain, the steady state error is 0 directly. No formula, nothing, all these things are not required. Type is greater than the power of the input signal. Now the steady state error is 0. Sir, is correct or not? We will check, we will verify. What is type here? Type is 1. What is power here? 0. Type is greater than power. Type is greater than power. What is the steady state error you are getting by doing the derivation? By using the formula, you are getting 0. And direct, what is the answer? 0. Is matching or not? And next, also you can check. Now, when type is less than, power of the input signal, when type is less than power of the input signal in time domain, when type is less than power of the input signal in time domain, now the steady state error is directly infinity, students. So that also you will verify. Type is how much? Type is 0 here. Type is 0. Now type is 0. What is the power here? Power is 1. Type is less than the power. Type is 0, power is 1. Type is less than the power. Then what is the steady state error? By doing the formula, by using the derivation, you are getting infinity, and I am saying directly the steady state error is infinity. Understand or not? Type is greater than, type is less than, there may be another chance. Now the another chance is nothing but type is equal to power of the type is equal to power of the input signal. Type is equal to power of the input signal in time domain. When type and power both are same, remember students, when type and power both are same, steady state error is a constant value. First you remember, when type and power both are same, steady state error is always a constant, and that constant value is A by K. Don't remember KA, KP, KV. It is a K, constant K. And this is A. Sir, that A value is how much? That depends upon the input. If it is a unit, that value is 1. If it is not a unit, it is having some slope. It is having some magnitude. It is having some constant. It is a step input, some magnitude, 10 or 20 or whatever. If it is a ramp signal, it is having some slope. It is a parabolic signal, it is having some value. But if it is unit step, unit ramp, unit parabolic, this A is directly 1. And here there is a special case. The steady state error is A by K when type and power both are same. Type 2, power 2, A by K. Type 1, power 1, A by K. Sir, where is A, sir? Here is A. This is A because unit means A is 1. Unit means A is 1. Understand not? Type 2, power 2, A by K. Type 1, power 1, A by K. Type 0, power 0, A by K. No, A by K plus 1. This is the only special case you have to be identified when type and power both are same. When type and power both are same means there is a special case, type 0 with step input, step or unit step input. Type 0 with step or unit step inputs means type is 0 and power step input means or unit step input means power is 0. When type and power both are same and that too power equals 0, type equals 0, now the steady state error is a by 1 plus k. This is the only special case. Type and power both are same. First point is answer is constant. Answer is constant. Answer is constant. But when type 1 power 1, type 2 power 2, type 100 power 100 a by k, but type 0 power 0, this is a by 1 plus k, because k equal to 3, a by 3 here. If k equal to 3, a by 3 plus 1, a by 4, that's why answer is changing. Okay, therefore you just remember this is a special case and everything will be same. Don't confuse on ka, kv, kp, that is constant. You have to identify that constant, and how to find that constant I am giving one shortcut method for that also, therefore not a issue. So kp, kv, ka, you remember the formulas, but while doing the steady state error calculations, remember it as k. It is a constant k. How to find that constant we will see. Now first you take a copy of this one, and before that you just fill these blanks. Now type 2 power 0, type is greater than power, steady state error is 0. Type is greater than power, steady state error is 0. Type is less than power, steady state error is infinity. Type is less than power, steady state error is infinity. All are clear. Okay, note on this. Now, students, one important point, I left the sixth point now. Then that sixth point, then you try to concentrate it. Now, first I want to clarify once again. Now, unit step input steady state error is 1 by 1 plus k. Unit ramp input steady state error is infinity. What you can understand? When input is changing, steady state error is changes. Clear or not? Next, type 0 steady state error is constant. Type 1 steady state error is 0. When type is changes, here is infinity, here is constant. When type changes, steady state error is changes. Steady state error depends upon input, steady state error depends upon type, hence it is proved. Next important point I am saying, now you put one constant input. Take this as a constant, this input as a constant, and type 0. Type 0, what is the steady state error? Infinity, right? Now type 0 is become type 1. Type 0 will become type 1 means type is increasing or decreasing? Yes, type is increasing. Type 0 will become type 1. Type is increasing. Infinite will become finite. infinite will become finite, and again type 1 will become type 2. Type 1 will become type 2 means type is again increases, and this finite will become 0. What you can understand? For a constant input, when type increases, steady state error is steady state error infinite, finite 0, decreases. Here is also for constant input, type 0, here answer is constant, type 1 this constant will become 0. Very very important point. So for a constant input, when type increases, steady state error is decreases. This is the important point. When type increases, steady state error is decreases. This is very very important. When type increases, we want always the steady state error should be less, minimum 0. So if you want a less steady state error, you should be increase the type. So what is the relation between steady state error and type? The steady state error and type is inversely proportional. Inversely proportional. When type increases, the steady state error is decreases. When type increases, steady state error is decreases. So how the type is increased? The type is increased by adding the number of open loop poles available at origin. By adding the number of open loop poles available at origin such that type increases. When type increases, steady state error is decreases. Understand not? When type increases, steady state error is decreases. Now that is the 6th point. All these points are very 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 important. Now depends upon input only for unity feedback and no steady state analysis for impulse, and depends upon type, and when type increases, steady state error is decreases. So students, you note down that.